Hello everyone. In the last lecture, we discussed the general purpose registers of 8086. Then we discussed the flag registers. Then we see the segmentation of the memory. Then segmentation registers. And last we discussed the pointer and the index registers. So they are all the registers which are used in 8086 microprocessor, and all the registers are of 16 bit. And also we showed how to generate the 20-bit physical address. So because every time when we have to access the memory, we require the 20-bit address, but our registers are of 16 bit. So BIU, bus interface unit, generate the 20-bit physical address by using the contents of the segment registers and the offsets which are stored in different registers. Now in this lecture we start with the pin diagram of 8086 microprocessor. So again, the 8086 microprocessor is 14 pin IC, and it requires the plus 5 volt supply for the operation. Now 8086 microprocessor is working in two modes. One is the minimum mode and another is the maximum mode. And the minimum and the maximum mode is decided by the pin number 33. The pin number 33 mentions the MN/MX bar mode. So if 1 is applied at the pin number 33, that means the 8086 is working in the minimum mode, and when 0 is applied on this pin, then the 8086 work in maximum mode. So what is the minimum mode and the maximum mode? So the in the minimum mode, the microprocessor is working in the single processor mode. That means in the system we have only the one processor, that is 8086 microprocessor, and that has all the controls of the buses and the signals, and the remaining component in the system are the latches, transceivers, clock generators, memory, and the input output devices. So the minimum mode is the mode of 8086 microprocessor in which only one microprocessor is working in the system. Now in the maximum mode, more than one microprocessor is working in the system. So in the same system we have multiple core processors in combination with 8086 microprocessor. So this 8086 microprocessor maximum mode will be operated when we apply the 0 at the pin number 33, and in this case the status signal S2 bar, S1 bar and S0 bar is used to provide the various control signals. And another chip called the bus controller derives the control signal uses this status information. तो इसमें क्या करता है कि जो ये माइक्रोप्रोसेसर है वो इन स्टेटस सिग्नल्स को जनरेट करता है, और एक और जो इसमें हमारा चिप लगा होता है जैसे हम बस कंट्रोलर कहते हैं, वो इन स्टेटस सिग्नल्स के अकॉर्डिंग बाकी जो कंट्रोल सिग्नल्स हैं उनको जनरेट करता है। ठीक है, तो ये हमारे मिन और मैक्स मोड हो गए। इन द मिनिमम मोड सिंगल प्रोसेसर इज वर्किंग, एंड इन द मैक्सिमम मोड more than one processor is working. So the pin diagram or the pin configuration of 8086 microprocessor is divided into three categories. In the first category we consider the signals that are in general used in both the modes, and second category we consider the signals that are working in the only the minimum mode, and then we consider the signals that are only working in the max mode. So the pin number 24 to 31, these pin numbers or these signals are work in both the mode. ठीक है, 24 से लेके 31 जो हमारे ये पिन हैं, ये हमारे दो मोड्स में वर्क करते हैं। इनमें ही हम मेन मोड में अगर हम वर्क कर रहे हैं तो दीज सिग्नल्स आर अप्लाइड इफ़ यू आर वर्किंग इन द मिनिमम मोड, एंड इफ मैक्सिमम मोड में अगर वर्क हो रहा है देन दीज सिग्नल्स विल बी अप्लाइड, and the remaining signals will remain common in both the minimum mode and the maximum mode. So the difference is only between the pin number 24 and 31. Now we consider first the general signals. Now as we know that in 8086 microprocessor we have the 20-bit address lines and we have the 16-bit data lines. Now again the 16-bit data lines is multiplexed with the 16-bit address lines. So the A0 to A15 address line is multiplexed with D0 to D15 data lines. So we have the multiplex bus, that is AD0 to AD15. So again when these lines will be separated by using the ALE signals. When the ALE signal is 1, again these lines are used to carry the address, and if ALE signal is 0, when the ALE signal is 0, then these lines are used to carry the data. So every time when we start the operation, then during in the initial cycle, this this bus are used to carry the address, and for the remaining cycle it is used to carry the data. Again we demultiplex these bus externally by using this ALE signal. Then again the remaining A16 to A19 lines are also multiplexed with the status line S3 to S6. This one. So we have the AD0 to AD15, that is multiplex data and the address bus. Then A16 to A19 is also multiplexed with the status signals. So A16 is multiplexed with S3, A17 is multiplexed with S4, A18 is multiplexed with S5, A19 is multiplexed with S6. So these lines are multiplex. So again these lines are used to carry the address, as well as these lines are used to carry the status signal. Now in this S6 is always remaining 0. That means S6 is not used for any function. So S6 is always remains 0. Now S5 indicates the condition for the interrupt flag. Again in the initial cycle these lines are used to carry the address, and for the remaining cycle they can be used to generate the status signal. So S5 is used to indicate the condition of the interrupt flag, whether the interrupt flag is enabled or disabled, that will be indicated by S5. Then S4 and S3, these two status signals indicates the segment being accessed during the current bus cycle. That means by S4 and S3 it is indicated that microprocessor is currently communicating with which segment. So if it is 0 0, then the microprocessor is communicating with the extra segment. If it is 0 1, the microprocessor is communicating with stack segment. If it is 1 0, it is communicating with code segment, that means it fetches the instructions. Or if microprocessor is not doing any function, then we can also say that microprocessor is communicating with no segment. Then if it is 1 1, then the microprocessor is communicating with the data segment. So by S4 and S3 it is indicated that microprocessor is currently accessing which segment. Then we have the RD bar signal. This RDY signal again, it is the active low signal. So when it is at logic 0, that means the microprocessor is receiving the data from the memory or the input output device. Then we have the ready signal. The ready signal means when the microprocessor is communicating with the slower peripheral device. Then this is the input output or the memory send the acknowledge through this pin. If the input output or the memory device is ready for the communication, then it send a acknowledge signal through this pin. So when this is high, it indicates that the peripheral is ready for the transfer of the data. So this ready signal indicates that the peripheral is ready to transfer the data. Then we have the INTR signal. This is again the interrupt request signal that is again generated by the peripheral device when it wants to communicate with the microprocessor. Then we have the test bar signal. Now this test pin signal is the input signal that is tested by the wait instruction. That means when the microprocessor is executing the wait instruction, then it has to check the status of the test pin. Now if the test pin is at the logic 0, then the microprocessor will do its normal operation. That means it does not go into the wait state. If the test pin is at the 0 logic, then microprocessor do its normal operation. It do not go into the wait state. But if the test pin is at the logic 1, that means the microprocessor has to wait until the test pin becomes 0. Okay. So this pin or this test pin input signal is checked during the wait instruction. If it is at the 0 level, then microprocessor will not go into the wait state. It will perform its normal operation. If it is at the logic 1, then the microprocessor will go into the wait state until the test becomes 0. Then we have the NMI, that is the non-maskable interrupt signal. This is similar to the INTR, except that any NMI interrupt does not check for the interrupt flip-flop or the priority. Okay, because it is the non-maskable interrupt, it cannot be ignored or delayed. So when this interrupt signal is generated, then it do not has to check whether the interrupt enable flip-flop is enabled or disabled, and what are the priorities among the interrupting signals. So when these signals are generated, microprocessor will accept this signal. Then we have the reset. Again, when the reset pin is applied, then the microprocessor will go into the wait state. Then we have the clock. This is the clock pin that is connected to the clock generator. This clock signal is used for the synchronization. Then we have the VCC. So plus 5 volt is applied at this pin with respect to the ground. Then we have the MN/MX bar. So if it is 1, then the microprocessor will work in the minimum mode. If it is 0, then the microprocessor will work in the maximum mode. Then the last signal which we used in general purpose is BHE bar or oblique S7. This BHE means bus high enable. Bus high enable is used along with the A0 bit of address lines to select whether we want to do the operation or we want to read the 8-bit or the 16-bit data from the memory. So if bus high enable signal is enabled, then the most significant data, that is D8 to D15, will be read during the read and write operation. In later slide, we explain how this BHE bar along with A naught is used to read or write the 16-bit data or the 8-bit data depending on the value of BHE bar and A naught. Then S7 is always remaining at 1. So these are the signals which are generally used in both the mode, whether it is minimum mode or it is the maximum mode. Now we consider the signals that are specifically used in the minimum mode. So in this, first we have the M oblique IO bar. When M oblique M IO bar, so when this signal is 1, then the microprocessor will communicate with the memory. If it is 0, then the microprocessor will work or communicate with the input output device. Then we have the WR bar signal. The microprocessor is used to write the data to the memory or to the input output device. Then it has to generate the WR bar signal. Then we have the INTA bar signal, that is the interrupt acknowledge signal. Then we have the ALE, that is the address latch enable, that is used to latch the higher order that is used to latch the AD0 to AD15 address oblique data bus in the external latch. That means by this latch we separate the multiplex bus, so it is used to demultiplex that bus. Then we have the DT oblique R bar. So DT oblique R bar means data transmit or receive. So this indicate whether the data will be received or transmitted. So this shows that the microprocessor, that the database is transmitting or receiving the data. So if it is 1, then the database is transmitting the data. If it is 0, the microprocessor or the database is receiving the data. So this is used to control the buffer. तो बफर को कंट्रोल करने के लिए हम इसे यूज़ करते हैं. तो आउटपुट बफर हमारा यूज़ होगा व्हेन द microprocessor will transmit the data, and input buffer will be used when it receives the data. Then we have the hold signal. Then hold signal is again used in the DMA case. So when the DMA controller generate the hold signal, then microprocessor will give up the control of its buses to the DMA controller. Then DMA controller use these buses to directly transfer the data between the system memory and the external device. Then when the microprocessor accept this hold request, then in acknowledge to this, it generate the HLDA hold acknowledge signal. Then we have the DEN. DEN is data enable bus. This activates the external data bus buffers. So as we say in the system, we have the transmitter bus. So this DEN is used to activate the external data bus buffers, that is the trans receivers, to receive the data or send the data. So these are the signals which are specifically used in the minimum mode. Then next we consider the data. These are the signals which are specifically used in the minimum mode. Then we consider the signals that are specifically used in the maximum mode. So these are the signals which are used in the maximum mode. RD bar, RQ oblique GT bar, RQ oblique GT bar 1 0, log bar S2 S1 S0 bar, QS0 QS1. So these are the 24 to 31 pin that are specifically used for the maximum mode also. Now first of all we show the status signals. So that is the S0 bar, S1 bar and S2 bars. these signals indicate the functioning of the current bus cycle. That means this indicates that in the current bus cycle microprocessor is performing which function. Then according to this status signal, the external device will generate the control signals. So if it is 000, then the interrupt acknowledge signal will be generated by the control lines. Then 001, it show the operations. So if it is 000, then interrupt acknowledge operation will be performed. If it is 001, input output read will be performed. That microprocessor will read the data from the input device. 010, the microprocessor will write the data to the output device. 011, it is the hold state. 100, the opcode fetch, that means microprocessor will fetch the instruction from the code segment. 101, microprocessor will read the data from the memory. 110, microprocessor will write the data into the memory. 111, it is the passive state, that means in this state it does not perform any function. So these, according to this status signal, the control device will generate the control signal accordingly. Then we have the RQ oblique GT1 and RQ oblique GT0. This is RQ request. So this is the request oblique grant signal. So these are the request for the direct memory access during the maximum mode operation. So as in minimum mode, hold signal will be used to for the DMA controller. So in that case of maximum mode, RQ oblique GT bar will be used for the direct memory access. So RQ request is generated and grant means the grant will be given by the microprocessor. Then log bar, the log output is used to log the peripheral of the system. Okay, if log output will be generated, then it logs the peripheral, that means it do not perform the communication with the peripheral. Then we have the QS0 to QS1. This will show the queue status. This bit show the status of the internal instruction queue. In the later slides we show how the queue will be used to hold the instructions for the microprocessor. So if it is 00, then no operation is performed. If it is 01, 1 byte of opcode from the queue will be read. If it is 10, that means the queue is empty. If it is 11, then the subsequent byte from the queue will be read. So if it is 00, then that means no operation is performed. That means microprocessor will not access the queue, instruction queue. If it is 00, then the first byte of the opcode from the queue will be read. If it is 10, that means the queue is empty. If it is 11, then the subsequent byte from the queue will be read. So these are the signals which are used in the maximum mode. RQ oblique GT1, log bar, S2, S1, S0, and QS and Q0. So these are the signals which are specifically used in the maximum mode. So these are the two modes in which the microprocessor will work: minimum mode and the maximum mode. Now next we consider the memory banking in the microprocessor. As we know that in any memory location we can store only the 8-bit data, but 8086 microprocessor is of 16-bit. That means it requires either the 16-bit data or 8-bit data. So if a single memory is used or a single memory chip is used, so at a time we can access only one memory location. That means at a time we can read only the 8-bit data from the memory. So when we require the 16-bit data, so that means it requires the 2 cycles to access the 16-bit data from the 2 different memory location. That means at one cycle we read this data, at the another cycle we read the next data, the data from the next memory location. Now the solution of this problem is memory banking. Now what is the memory banking? So in the memory banking, the memory chip is divided into two banks. One is known as the odd bank and another is known as the even bank. In the odd bank, the addresses of each memory location is odd, and in the even bank, the address of each memory location is even. So the one bank contains the even addresses, that is called the even bank, and another contains the odd addresses called the odd banks. So physically 1 MB memory is divided into two parts. This is 512 memory, 512 MB KB memory, and this is again 512 KB memory. So overall we have the 1 MB memory, but it is physically divided into two banks. One is known as the odd bank and another is known as the even bank. Now depending on the BHE bar signal and A0 signal, we enable one of the bank or both of the bank at the same time. So if we want to read the data or write the data of 16 bit, that means we want to transfer the 16 bit data, then BHE bar will be 0 and A0 will be 0. A0 is 0 means we read the data from the even bank, and when BHE bar is 0, that means we read the data from the odd bank. So if both are 0, that means we read the data from the even bank, also from the odd bank. So this is 0 0 0 0 0 5 0 and this is 0 0 0 1. Okay? Similarly this will extend it. So we read first the data from the even bank, then we read the data from the odd bank. So total 16 bit data will be read in this case when BHE bar is 0 and A0 is 0. So A0 is 0, that means we read the data from the even bank. If BHE bar is 0, then we read the data from the odd bank. Then if it is 0 1, so 0 1 means we read the data from the higher bank. And a higher bank means odd bank. So even bank is known as the lower bank and odd bank is known as the higher bank. Okay, so if it is 0 1, that means this is enabled. So we read the data from the odd bank, that is the higher bank. If it is 1 0, that means this even bank is enabled. So we read the transfer the data from the higher bank when it is 0 1. BHE bar is 0. When it is 1 0, we transfer the 8-bit data from the lower bank, that is the even bank. And if it is 1 1, that means we do not transfer the data from the memory. So this is how the microprocessor is capable of reading the 16-bit data or 8-bit data in the one cycle through the memory. Now in the next lecture we consider the internal architecture of 8086 microprocessor.